Hi everyone, welcome to the third week of Incomplete Data Analysis. In this week, we will learn about naive methods for handling missing data. And these methods, although naive or somehow ad hoc, they are still widely used in practice, and so they deserve our attention. These methods can be divided in two classes. The first class of methods deal with missing values by removing any individuals with incomplete information. And the second class of methods deals with missing values by filling in or imputing the missing values. And for each missing value, we will impute a single value and therefore the name single imputation. In this part, we will be focusing in the first class of methods, the methods that disregard data from individuals with missing observations, and we will learn about two methods, complete case analysis and available case analysis. But a small apart before going ahead, we will be mentioning that some of the approaches have the potential to induce bias or that they lead to biased estimators, and so it's not possibly a bad idea to define what is the bias of an estimator. And to do that, suppose that we have y1 up to yn independently and identically distributed random variables, each of them with probability density function or probability mass function, depending on whether they are continuous or discrete, given by f, which is parameterized by some parameter theta that it's unknown and that we want to estimate from our data. Let us define theta hat as a function of our random variables y1 up to yn, and the bias of theta hat is nothing more than the difference between the expected value of theta hat and the true value of the parameter theta. And so we define bias by this quantity. The bias of our estimator theta hat is equal to the expectation of theta hat minus the true value of the parameter, which is theta. And we say that the estimator is unbiased if the bias is 0, and so if the expected value of the estimator equals theta. That's exactly what we have here. Otherwise, the estimator is said to be biased. And let's do an example. Suppose that we have y1 up to yn, that they are IID from a normal distribution with mean theta and variance 1. Let us think about an estimator for theta for the mean, and a natural one would be the sample mean. And now the question is the sample mean, is our theta hat unbiased for theta? So what we are asking is the expected value of theta hat equal to theta? So let's compute this expectation. So expectation of theta hat is, our theta hat is the sample mean. 1 over n is a constant, so I can put it outside of the expectation. Sorry, outside of the expectation, and then I don't need it inside, right? And by the linearity property of the expected value, I can write it as the sum of the expectations, and now I know that each of them has expected value given by theta. And so, yes, the sample mean is an unbiased estimator for the mean, okay, in the normal distribution. And okay, let us start. Complete case analysis. We have already talked about this approach in the past weeks, and basically complete case analysis, also known in the literature as listwise deletion, excludes the data for any individual that has one or more missing values. So the data are treated as if the cases with missing values were simply not there. And in the table below, an hypothetical data set, or the first rows of an hypothetical data set, we have that only the first individual has complete information on all three variables. So under a complete case analysis approach, individual number 2, 3, and 4 would be excluded from our analysis because they don't have complete information. And this method, complete case analysis or listwise deletion, is maybe unfortunately still one of the most used in the applied sciences. And okay, what is the convenience, or why is it so popular? If we restrict our analysis to those with complete information, so we eliminate the need for missing data handling procedures, and we can use basically any procedure that we already know, and we do not also need any specialized software, as the software that we have available will deal with the complete data as they would deal with any other data set. But okay, what are the costs associated to this simplicity? Well, if the data are missing completely at random, we know that the observed data can be regarded as a random sample of the complete data, and so the inferences under a complete case analysis approach, they are valid in the sense that they lead to unbiased estimators. But although they lead to unbiased estimators, since we are working with a reduced sample size, the standard error of our estimates will be larger compared to what they would have been if we had observed the complete data set. So the standard errors, they are valid for our reduced subset of data, but it's not hard to think or to imagine that if we had more data, if we had the complete data, our information would be more precise. So the standard errors associated with a complete case analysis are larger than those of the estimates that would have been obtained from the complete data. And also we must be aware that this approach is potentially wasteful, because if we have a very large number of variables that we are interested in collecting information about, it's very likely that some of the individuals will have at least one missing value for one of the variables, and so this would possibly lead to eliminating several individuals, and so we may end up with a very reduced sample size. In case we have a large number of variables, it's likely that some individuals will have a missing value in one of the variables, and so our data set will be possibly under a complete case analysis a much shorter version than what it would have been in case there were no missing values, because we are eliminating the individuals with missing values. We are just disregarding them from our analysis. So basically, main point, if data are missing completely at random, a complete case analysis lead to unbiased estimators, although the estimates are not very efficient, because since we are working with a reduced sample size, the standard errors of the estimates will be larger compared to those that would have been obtained with the complete data set. And also, if we have many variables, it's very likely that individuals will have missing values for one of the variables, and so we may end up with a very reduced sample size. And okay, a natural question to ask is, okay, is there any threshold below which threshold on the number of individuals with missing observations below which it's reasonable to follow a complete case analysis approach? And well, there are answers for all cases. One of the authors, Anders is the author of the book Applied Missing Data Analysis, that is on our reading list. He says that in most situations, the disadvantage of listwise deletion far outweigh its advantage. So it's not a fan of complete case analysis. On the other side, Graham in 2009 in a review paper about missing data methods published in the Annual Review of Psychology. He said that, well, in case he had, for instance, only 5% or less of missing cases, he would still follow one of the approaches specialized for dealing with missing data, and we will learn about them. They are maximum likelihood or multiple imputation, but he says that if a researcher chooses to use complete case analysis in the case he or she only has a data set with 5% or less than missing values, then maybe we cannot criticize such options. So you see that two different answers to the same question. I think at the end it's up to us. Of course, if we have a lot of missing values, it's clearly not a good approach. If we only have a few missing values, also depending on where they occur in the data set, maybe we can go with a complete case analysis approach. And okay, what should we be aware about complete case analysis? Well, we have seen that if the data are missing completely at random, that the estimates, although not efficient, they are unbiased. But even if data are only and only between quotations missing at random, inferences from a complete case analysis can be biased. So missing completely at random, unbiased but inefficient, and missing at random or missing not at random, they will be biased. But in fairness, and also connected to the previous slide, that some author says that you should never use a complete case analysis. And again, in fairness, complete case analysis is not always a bad option. There is a very specific, it's very specific, but there is one situation where following a complete case analysis approach will give you better or will outperform more advanced approaches for dealing with missing data, like maximum likelihood or missing imputation. And the context is the following. The complete case analysis can produce unbiased estimates of the regression coefficients under any missing data mechanism, be it missing completely at random, missing at random, or missing not at random, provided that the probability of observing a complete case, and hereby a complete case we mean an individual for whom both the response variable and the covariates are observed, is a function of the covariates and not of the response variable. So this is like a general result that says that under these conditions, complete case analysis is a valid approach. It leads to unbiased estimates of the regression coefficients, and it's likely to outperform more specialized techniques like maximum likelihood and multiple imputation. We will look at this result in the next workshop, in the workshop 2 in week 4. But okay, that we should also be aware that although in this case missing complete case analysis gives unbiased estimates of the regression coefficients under any missing data mechanism, provided that the chance of observing a complete case is a function only of the covariates and not of the response variables. This is a very particular case, and in general, more specialized techniques will outperform a complete case analysis approach. But okay, you should be aware that there exists a scenario where complete case analysis is a valid approach regardless of the missing data mechanism, and we will look at this result, as I said, in more detail in the next workshop. And okay, now let's move to the other approach that is also listed in the class of approaches that disregard individuals with missing observations, and it is known as available case analysis or pairwise deletion, and it somehow attempts to mitigate the data loss problem of complete case analysis. So under an available case analysis approach, different aspects of a problem are studied with different subsets of the data. And the typical application of available case analysis is in the calculation or computation of covariances and correlation matrices. And So let us put ourselves in this context in the calculation of correlation and covariance matrices. And as a toy example, suppose that we have two variables, x1, x2, and that x2 is subject to missingness while x1 is always observed. And so we know that this is a univariate pattern, so we can rearrange the data set in such a way that as we have it here, the first m, say, individuals, they have observed x2 values, while the remaining n minus m individuals, they have missing values for x2. So we know that for the first m individuals, they have both x1 and x2 observed, while for the remaining n minus m, only x1 is observed. So under under an available case analysis approach, if we want to compute the mean of x1, we will use all individuals. If we want to compute the mean of x2, we will only use these m individuals. The same for the variance of x1 and the variance of x2. And this is by opposition to a complete case analysis approach, because a complete case analysis approach says that these are eliminated. So we are, when computing the mean of x1, only the first m individuals contribute to our mean, whereas in an available case analysis, all individuals contribute to the computation of the mean and of the variance, okay? And what we should be aware is that when computing the covariance between x1 and x2, only the pairs of individuals that are completely observed will contribute. So we will only use this to compute the covariance or the correlation between x1 and x2. And this is exactly what we have here. If we are interested in the in computing means, variances, and covariances, we have that for the mean of x1, since it's complete, all n individuals contribute with information. For the mean of x2, only the first m individuals, that this corresponds to those that have available data on x2. For the variance of x1, we use all n individuals. For the variance of x2, we only use the m individuals. And now here in this expression, the estimated or the sample covariance between x1 and x2. This is the general expression, but note that here we are using the mean of x1 and we are not using all n individuals that are available, but only the data for the first m individuals for x1. M individuals that have complete information on x1 and on x2. You could still use or there are softwares that compute the covariance matrix under an available case analysis, that here they do not use x1 of m, so the first m individuals, to compute the mean of x1, but they use it from the complete, they use the complete information to compute the mean and to impute it here on the expression of the sample covariance. But this in general can be problematic. So it's better, still has some problems, but it's better than when computing the covariance or the correlation between the different pairs. We just use for the mean of the variables. Even if we have more data, we just use the observed values for the values that have available information on both variables. Okay, we will make this more concrete in a second. And okay, then we would, you know, that the covariance matrix, the diagonal are the sample variances, and the off diagonal are the covariances. In this case, we only have two variables. So in the off diagonal, we have the covariance between x1 and x2. And from this information, we can also compute the correlation between x1 and x2. It's here, it's just the covariance between x1 and x2 divided by the variance of x2 and the variances of x1. And again, for the variance of x1, we are just using the first m individuals. And this method is simple. It uses all available information for the different pieces that we are calculating. When calculating the mean or the variance, in this case of x is 1, we use all information for x is 1. Then when calculating the mean and variances for x is 2, we also use the information available for x is 2. And when computing the covariance or correlation between x is 1 and x is 2, we just use the data for which both variables have complete information. And it's simple, uses all available information, and it can be shown to produce consistent estimates of mean correlations and covariances if data are missing completely at random. And this is stated in the book by Little and Rubin, Statistical Analysis with Missing Data, on page 55. And consistently with complete case analysis, available case analysis lead to biased estimates if data are not missing completely at random, if data are missing at random or missing not at random. And also, because the way it works, available case analysis has a number of problems that limits its utility in practice, and possibly one of those problems, or the major of such problems, is that it can lead, because we are using different subsets of the data to compute the covariance matrix. In a way it is good because we are making use of all the information that we can, but also because we are using different subsets of data for different quantities. One of the associated problem of this is that the resulting covariance matrix may not be positive semi-definite, and this is a requirement if you then want to use this resulting matrix in, say, principal component analysis or factor analysis. They require that the covariance or the correlation matrix is positive semi-definite, and if it's not, you cannot proceed with your analysis. And to make ideas more clear, let us consider the hypothetical data set that we have listed here. We have three variables, y1, y2, and y3, and they all have missing values occurring in a random they can occur in any of the three variables for any of the individuals. So in terms of missing data pattern, this is a general missing data pattern. And okay, now we will compute the covariance matrix under a complete case analysis approach and under an available case analysis approach. So I will just show you how to compute one of the first entries. So let's start with a complete case analysis approach. With a complete case analysis approach and the covariance matrix, as we have it here, it has on the diagonal the variance of y1, the variance of y2, and the variance of y3, and on the off diagonal, for instance, in the first row, it has the first row on the second column, it has the covariance between y1 and y2, and on the third column, the covariance between y1 and y3, and so on and so forth for the other entries. And okay, complete case analysis, we know that we will eliminate from our calculations all individuals that have at least one missing values for one of the variables. And so if we look at our data set, we only retain this individual because this individual has observed values for all three variables, and the last individual, right? All the others are eliminated from our analysis. And so we will base our calculations on only these two individuals. And okay, let me reproduce one or a couple of the entries. So we know that I don't have here the matrix now, but you have it, or you can print the slides and look at it. So I know that the mean of y1 is just this, and also, and if I want to compute the variance, the sample variance of the variable y1, I know that using the expression, it's this okay, and I have reproduced the first entry. It's the same for all the other variances, and for instance, the covariance between the sample covariance between y1 and y2 is nothing more than and so we also have reproduced this value here, and it's exactly the same for all the other entries. Okay, so you can do it by yourself, and in the next video we will also see how to do it, how to do this automatically in R, so we don't have to do all the calculations by hand, but it's good that we know what R is doing. Okay, so complete case analysis, it's easy. We just remove all individuals from our dataset that have at least one missing value for one of the variables, and we retain those with complete information on all three variables. In this case, this is a toy or hypothetical dataset, so it's a very small one, and in this case it happened that only two individuals had complete information on all three variables. Now let's try to compute again the covariance matrix, but now under an available case analysis. So an available case analysis, first for the variance of y1, I will use these individuals and these and this, right? Whereas for the variance of y2, I will use this, 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 and these individuals, and for y3, the same. This is for the variances, okay? So I will now just, as an example, compute the variance of y1. So the variance of y1, how many individuals do I have? 3, 5, 7. I have 7 individuals with available information on the y1 variable, and I will use the information from all of them to compute the variance of y1, to reproduce the first entry of our covariance matrix. And so if I do this, I know that I've just written down here. So and this is the mean, of y1 is 23. And now the variance is just 1/6. Sorry, this is 26, okay? So hopefully I put all the numbers correctly, and this is rounded to 2 decimal places, equal to 6.67. And okay, I have computed the mean of y1 and the corresponding sample variance, the sample mean and the sample variance. Now I want to reproduce this second entry. It's the sample variance between y1 and y2. And okay, now, sorry, I'm just going back and forth on the slides, but okay, now for computing the covariance between y1 and y2, I will look for all individuals that have complete information on both variables. And so I will retain this one, this, oh, sorry, not this one, this one. So I'm retaining 4 individuals, right? That have complete information on both y1 and y2. And now what I will need to do is again to recompute the mean, but now of y1 using only these 4 individuals, the mean of y2, and then I can compute the covariance between the sample covariance between y1 and y2. So I will write of 4, and it's I've made this before, right? It's not from my hand that I know what these means are. So I have this, and now I can compute the covariance, the sample covariance between y1 and y2. Sorry. Sorry. Rounded to 2 decimal places, we obtain 24.33, and I hope that I have not messed up in the calculations. Sorry, here the result is correct, but I've just checked that here it's 20. The final result, it's okay because I've just put it wrong here, and so here it's also 20. And okay, main point is that for computing the sample covariance between y1 and y2, we look at those having complete information on these 2 variables, and we compute the sample covariance based on this data. And so the mean that we are using here for y1 and y2 are different than the mean that was used to compute the sample variance, okay? It's just a subset of the individuals. And with this, we replicate this entry, and all the others you can obtain them in a similar way. It's kind of tedious, and that's why we will learn how to do this automatically in R. And as we will see, while the covariance matrix, this one under a complete case analysis, is semi-positive definite, this one under an available case analysis, we will see that it's not. So if we would like then to use this covariance matrix for, say, a principal component analysis approach, we couldn't, or we would run in trouble. And okay, that's it for this part. We have learned about complete case analysis, where any individual with only a single value will be discarded from our analysis, and we know that under a missing completely at random, this leads to unbiased, although inefficient estimates, and available case analysis somehow tries to mitigate this loss of data and tries to use all available pieces of data to compute. And the available case analysis is basically used for computations of covariance and correlation matrices, and basically try to use all available information for the different quantities. But it may lead to, although it leads under missing completely at random to consist to unbiased or even consistent estimates of the different quantities, it can, because in some situations it can lead to covariance matrices that are not semi-positive definite, and we may run into trouble. But okay, that's one of the problems. It's well known. Sometimes it limits its utility, but that's the approach. And okay, that's it for this part. We will see how to implement this in R, and then we will learn about single imputation approaches. They also have their drawbacks, but somehow they form the basis for more advanced methods, so it's worth learning them. So thank you, and see you in the next video.